Hello and welcome to the second section of Optimization AMS 2940. Today we're going to be we're going to jump right into how to solve how to solve linear programs where we're going to do it by computer through Microsoft Excel. So at this point, if you don't have Microsoft Excel yet, you can get it through the university. You will need it, or it will be a very good idea to have it for solving these linear programs. What we're going to do today is step through how to use it for solving it. There are other ways to solve these. So part of the course isn't to know Microsoft Excel, but it is part of it is knowing how to solve linear programs using a computer. So if you prefer to use one of the other pieces of software out there that does it, there's all kinds of them. Ample, MATLAB can solve it. There's all kinds of different programs out there, and you're more comfortable with that, you're welcome to do that. Microsoft Excel is something that is provided by the university and is very common, so I'm going to use that as our main means of solving linear programs during this course. So let's step through a computer solution with Solver. Now you should recognize this. This is the linear program that we solved last class. And to refresh your memory, the solution for this was x1 equals 5, x2 equals 5, and c equals 40. That was the maximum for our objective function. So let's see how we solve this with Microsoft Excel. Again, Microsoft Excel actually has a very robust solver. You can solve fairly large systems of linear programs in it. This is a small one, 2 variables, but we'll use it as an example. So how do you access it? In Microsoft Excel, under the Data menu, there's something called Solver. I believe in Excel for Macintosh, it's still under the Tools menu, but it's again called Solver. So see if you have that. It's possible that your version of Microsoft Excel doesn't have it. If it's not showing, this is an add-in that you have to add into Microsoft Excel. So in Excel for Windows, here's the instructions. Under the File tab, click Options and Add-ins, and you look through it and find the Solver command. In Excel for Macintosh, it's the same thing. Under Tools, choose Add-ins. Under Add-in box, you find Solver. So it has to be added into Microsoft Excel if it isn't already there. So let's try set this up now. If you remember, in the system of linear equations, we really have a couple of components. There are 3 main components. We have our variables, we have our objective function, and we have our constraints. So here's what I normally do to start off when I'm using Microsoft Excel to solve things. My first column, I just put objective and constraints like that, just to keep them separate. What I'm going to do is I'm going to put my objective on one line, my constraints on multiple lines underneath. I give a column for each variable, in this case x1 and x2. If I had more variables, I'd add more columns for them. A column for the value, where we're going to calculate what our equation is equal to. And skip a column, which we will actually use, but then a column for limits. So you can set this up on Excel if you have it set up already. This is just the basic structure that I generally use to keep it organized. So now let's start putting our information in. Let's start with our objective function. That was our objective function. Maximize c equal to 3x1 plus 5x2. So what do? In the objective row, these blocks are going to be the value of my variable. And eventually, after we solve it, the optimal values are going to be put in there. But I just started with zeros. So I just put a 0 in for each of them. There are cases where you will start with something else, but for now, we'll just put a 0 in for them. Really, this is a first guess at it and lets you help set up the equation. The value box, this is the important one. This is where you actually put your objective function. So our objective function is 3x1 plus 5x2. The value for that box is 3 times b2. b2 is a value of x1 plus 5 times c2. c2 is the value of x2. That is the value of my objective function. So for instance, if I were to change x1 to something else and x2 to something else, this would automatically update with the value of that objective function at that point. It's very important when we do the solver that we have one box that says, at this point, the value of my objective function is this. Column E, I said we don't bother putting a header on it usually. You can if you want to. But here I kind of put a reminder that we are trying to maximize. So I make it a max. And there's my objective function. There's no limit on it. So there's my objective function in the spreadsheet. Next, we'll turn our attention to the constraints. So how do we put in the constraints? Well, we have two different types of constraints. We have these equations and we have the non-negativity constraints. Let's focus on these equations first. So let's put these in. We have 3 of them, so we need 3 rows for them. And here's my 3 rows in my constraint section. Now, if you look in each of these, you can see where I've got the equation embedded. Take our first one. 4x1 plus 2x2 is less than or equal to 32. Read across my first constraint. There's my coefficient 4 for x1, 2 times x2, and then I have my value. So the value again, and I've highlighted it here, you can see that this is exactly my equation, but I'm using the numbers that have been put in here. So it is b4 times b2. b4 is the 4 coefficient. b2 is the value of x1. So you can see by setting just the value of x1 to whatever you want, it will be reflected. Plus 2 times the value of x2, c4 times c2. There is the value of that constraint at that point. Okay, if you're not familiar with Excel, the little dollar signs here might be a little bit of a mystery. That's relative versus absolute referencing. That's something else that it's a good idea to get comfortable with that on your own if you aren't familiar with Excel. So now I've got my value of my constraint at that variable. My constraint says that it has to be less than or equal to 32. So I put in less than or equal to 32. And under limit, that's my limit for that constraint. And then just repeat for the other two. So I have one row for each of my constraints. I have one box that says at the value set for my objective or for my variables up here, this is the value of that left-hand side of the constraint. And then my limit saying I'm not allowed to go over this, or it could be greater than or equal to, saying I'm not allowed to go under it. Okay, so those are my constraints. So once I put in those constraints, the last two constraints are the non-negativity, and we're going to see that those are entered a little bit differently. I just kind of put a reminder down here to say that these things are going to be greater than or equal to 0. You can in Excel say that this variable is unconstrained. It's not, it can be both positive or negative. Excel allows that. So I just put in a reminder that these are going to be positive numbers or greater than or equal to 0. And there is my entire linear program put into a nice little Excel spreadsheet. Now the next step is tell Excel to solve this. And that's where the solver comes in. So when you click on solver, you get an interface that looks like this. It may look a little bit different for you depending on which version of Excel you have, or if you're using a Mac. This is on a Windows PC. So, but I'll show you the key components of it that you have to set. So the first thing we have to set is our objective function. We are told we have to make something as large as possible, subject to certain constraints by changing, and there's certain variables we can change. So first thing we're going to set is to set our objective. And that's equal to D2. That is the value of our function. That is our objective, the thing that we're trying to optimize. We are going to maximize it. So make sure it's maximize, minimize, or value of, depending on your linear program. It defaults to maximize, which in this case we are maximizing something. So you just leave it at maximum. And by changing variable cells. So what can we change? Well, you give it the whole row of items you can change. So in this case, B2 through C2. Those are the things that we're going to allow Excel to change to try and maximize our function. Everything else depends on those. Now, we have to enter in the constraints. So at this point, we have our objective function. We haven't told Solver what the constraints are yet, so it could blow up to whatever it wants. So we have to put in the constraints. That's the next box down here. So when you click on Add, you get something that looks like this to add the constraint. So what do we have to do now? Remember our constraint. Our first constraint was 4x1 plus 2x2 is less than or equal to 32. So but in our spreadsheet, the way that we set it up, we actually have a value which is 4x2 plus 2x2 for whatever variables are put in. So in our add constraint box, we set our cell reference equal to that value. So in this case, D4. The D4 is the value of that. The box here, you just choose less than or equal to, greater than or equal to, whatever it is. We just put that in there as a reminder of what it was. It doesn't actually do anything when you're using a solver. It was just a reminder to make sure that we select the right option here. And then our actual constraint, the limit, the thing that's holding us back, that is cell F4. So you choose F4, and that adds your constraint. You click on either OK, or if you click on Add, it'll just give you the same box again to choose the next one. So you do this 3 times, one for each of the constraints, and you end up with the 3 constraints in there. But we also had the non-negativity constraints. So do it 2 more times, and when you do it, you just select that your variable B2 and select greater than or equal to, and set the constraint, just type in the number 0. And you get that B2 is greater than or equal to 0. Do it again for C2. C2 is greater than or equal to 0. And that gives us all of our constraints. The 5 constraints we have are now in there. Now, one of the important things, select the solving method. It actually defaults to something else. What we're working with for now is the simplex method. So choose simplex LP. This is the fastest. Excel gives you 3 options. Simplex is the fastest one, but your program has to have a certain structure for it. We are only dealing with linear programs for now, so choose simplex LP. It is the fastest way of solving these programs. And that's it. Now you have it in there. You have your objective, that you're maximizing it, the things you can change, and your constraints. Those were the components of a linear program. At this point, if you're a little bit unfamiliar with this, there are all kinds of tutorials online on how to add a linear program into Excel. Practice it a couple of times if you need a little bit more practice. But now we're going to solve it. To do that, we just click on Solve. It's going to give us a couple more options. For now, we're going to leave the box at Keep Solver Solution. The reports, it gives you 3 options for reports. If you have more add-ins, it can give you more options, I believe, but for now, we only have 3 of them. Choose Answer. We are going to use the other 2 later in this course, but for now, just choose Answer because we're just trying to get the answer. And click OK. And it will solve it out for you, and you'll see it will solve this in a blink of an eye. It will give you the solution. So if you go back and look at your linear program, you will see the numbers have changed to x1 equals 5, x2 equals 5, and our value is 40. So it tells you that the solution is x1 equals 5, x2 equals 5, and c equals 40. That's your solution, and you'll see that it matches exactly with what we had with the graphical method. But when you do the answer, it also creates another tab, a whole new tab that gives you more information. So it gives you a tab called Answer Report 1, or 2 or 3, depending on how many times you do it. It gives you an answer report. And you can see in here, your objective value, we started with 0, because we had set everything to 0 to start. Final value of 40, c equals 40. That's as high as we can make our objective function. What variables do that? What are the variable values? That's the next set. So x1 equals 5 and x2 equals 5. There's the values of the variables. And finally, it gives you a section for the constraints. We're going to be getting into interpreting this a lot more, but for now, you can see that we have our 3 main equations in here. And here's one important thing to notice: not binding and binding. So it says our first equation is not binding. Our next 2 equations are binding. Those are the things that are holding you back from getting any bigger. The first equation isn't doing anything. It isn't stopping you from getting any bigger. What this is going to mean is that you could change that first equation for a little ways anyways. You could change that first equation and not change your answer. Your second and third equations, they're binding. As soon as you change those equations, you change your answer. That's getting into the sensitivity analysis, which we're going to be doing fairly soon. Then we have our 2 non-negativity constraints, both non-binding, which means, again, you could change those and not impact your answer. So that's solving by Excel. And with those binding and non-binding, if we take a look at the graph that we did graphically, we had figured out the 0.55, the value of our function was 40, and when it got to non-binding and binding, this is binding, and this is binding. If you were to change either of those lines, you're going to be able to slide your objective line in one direction or another, but your answer is going to change. The non-binding, that one. So that one was non-binding. The other 2 were binding. The non-binding one, you can see, you could change that line for a little ways and not impact your answer. If you change it in the left direction, eventually it's going to change the answer, but you can always slide it a little bit and not impact it. In real world problems, that's actually an important thing to know. Which of your constraints are the most important things? So if you can change your constraints, which ones do you focus on to make your answer better? All right, so that's an example of using Excel. Next class, we are going to start going through the simplex method itself to see how we do this by hand and what the solver is actually doing. But knowing how to use the solver is going to make your life a lot easier because there's a lot of tedious calculations in the simplex method. Excel takes care of those for you. But now we're going to talk about problem formulation. And I mentioned this in the last class that solving the mathematical side of optimization is only one part of optimization. The hardest part is often taking a problem, turning it into the mathematical equations that you can then solve. In the real world, it's usually pretty fuzzy. There are certain things you can do, certain things you can't do with it, but trying to come up with the equations is often the hardest part of what you have to do when you're solving these. So what I'm going to do is I'm going to step through, I think, 3 problems, written problems, and we're going to create the equations that form the linear program that we can then solve mathematically. So first one, an optimal diet. This is a dietitian preparing a diet of 2 foods, A and B. Each unit of food contains a certain amount of protein, fat, and carbohydrates. So that's food A contains a certain amount, food B contains a certain amount. But what are the costs? A unit of food A costs 60 cents and a unit of food B costs 40 cents. The diet being prepared has to contain a certain amount of protein, fat, and carbohydrates. So we are going to try to figure out how we can combine these 2 foods for the least cost. So let's start break this down a little bit. What are the things we have to do? What are the components? Optimization is about meeting an objective using the least resources possible. So, what do I need to optimize? What are the things I can change? What resources are required for the different options and what's holding me back? And our main things are the objectives, the variable, and the constraints. Those are the 3 main components I talked about. So in this case, what do we have? Optimal diet objective. So what is the goal? And you can usually write this out as a written statement, and it may seem fairly obvious, but it's a good idea to actually write this out just to make sure that you don't get a little bit confused later, because some of these programs, some of these interpretations can get a little confusing when you start adding in more things. So in this case, what do we want to do? We want to build a diet that meets minimal dietary requirements for the lowest cost. If you go back and look at the problem, that's what we're trying to do. We are trying to spend as little as possible and meet certain requirements. Certain amount of carbohydrates, certain amount of fat, certain amount of protein. Next step, the variables. What can I change? The only thing that I can change is that mixture. We're told that food A has a certain composition. We can't change that composition. We're told food B has a certain composition that we can't change. The only thing we can change is how much of food A and how much of food B. Those are the things we can change. Give those variables names. So let x1 equal the amount of food A and x2 be the number of units of food B. Not A, it's written there, the amount of food B. So those are the only things that I can control, the only things I have control over. Now, when you're writing this down, please write down your variable and what it means. Okay, it's hard to emphasize how important this is. Write down each of your variables and what they mean. So the cost, this is our objective statement. What is it that we have to minimize or maximize? It's sometimes called a cost function. We've been calling it an objective function, this term, and it's written in terms of the variables. So the variables are the things that you can change. This is the relation between, as I change these things, how does my cost change, or how does my objective change? Note if it's a maximize or minimize. In this problem, what do we have? We're trying to minimize the cost. So we're trying to minimize the cost. And what is the cost? Well, the only thing we have control of is the amount of each food that you take, the amount of food A and the amount of food B. Those are my two variables, x1 and x2. I'm told that x1, or food A, costs 60 cents per unit. So x1 is the number of units, and each unit costs 60 cents. So 0.6 times x1 is my cost that I'm spending on food A. Likewise, 0.4 times x2 is what I'm spending on food B. Add those together, that's my cost. That's how much I'm spending. It's the only thing I can control are those variables, the amount that I take of each. The cost that I'm spending is C. So there's my objective function. I am trying to minimize my cost. But now what's holding me back? Why can't I make this smaller? I'm told in my problem, I need to have a certain amount of protein, a certain amount of fat, and a certain amount of carbohydrates. And I just restated those here as bullet points. I need 60 grams of protein, 24 grams of fat, and 30 grams of carbohydrates. That's what I need. Put these in variables, in terms of the variables. Again, the only thing that I can control is the amount of each food that I buy. But my problem told me that every unit of food A has this much protein, fat, and carbohydrates. So from that, I can get my constraints. My first constraint, the first thing that holds me back, is that I need at least 60 grams of protein. So how do I know that I have that much? Well, each unit of food A gives me 20 grams of proteins. Each unit of food B gives me 30 grams of proteins. That's from the problem itself when it was first stated. So if I know what the value of x1 and x2 is, I can just add those up and I get the amount of protein that I've bought. And my problem says that has to be at least 60 grams. So there is my first constraint. The amount of protein that I buy is at least 60. There's my first constraint. Go on to my second constraint. My second constraint said that I need 24 grams of fat. Each unit of food A provides 12 grams of fat. Each unit of food B provides 6 grams of fat. Add them up, make it at least 24. There's my second constraint. The second thing holding me back. My third constraint, dealing with carbohydrates, same way. 30 times the amount of food A plus 15 times the amount of food B, and it has to be at least 30 grams. There's my third constraint. So the three things holding me back are now in there. And finally, the second type of constraint, non-negativity constraints, you can't buy a negative number of food, so both of the variables have to be greater than or equal to 0. And here is my formulation for the diet. Now, as an exercise, you can take this and put it into your Excel spreadsheet, practice using your solver, and what you should come out with in the end is x1 equals 1.5, x2 equals 1, and your cost, your minimum cost, is 1.3. So when you run it through your solver, you're going to get that to minimize your cost, you should buy 1.5 units of food A 1 unit of food B, and it will cost 1.3. So there's our first type of problem. That's a very straightforward problem. Now, minimizing cost is one common thing that you look at. Another thing you look at quite often in these problems is maximizing profits. So in this case, we're going to look at a car manufacturer who is trying to maximize the profit. So they are going to make two types of cars, Model A and Model B. Each car requires two operations, assembling and finishing. This is a very simplified version of a car manufacturer, obviously. Each car of Model A has a certain requirement for assembly and finishing in terms of time, and delivers a certain profit. Each car of Model B has a requirement for assembly and finishing and delivers a certain profit. So that's what's required, but what's holding them back? Well, we don't have infinite time to build these things, so what's holding back is that there are only 720 hours available on the assembly line and 480 hours on the finishing line. But we also have another one. They have promised to deliver 20 units of Model A and 30 units of Model B. So these are going to be our constraints. The things that are holding us back from just making arbitrary decisions, those are our constraints. So for the car manufacturer, let's see how we can turn this into a linear program. First, the objective. Determine the optimal mix of cars that meets minimum production requirements and maximizes profit. That's the overall plan of what we're going to do. Variables. What are the things that we can change? Again, write it out. X1 is the number of units of car A. X2 is the number of units of car B that are built. That's what we're allowed to change. Nothing else can be changed. Everything else is set in stone. What's our objective function? Again, we are told we want to maximize the profit. So we're maximizing P. And what is the profit in terms of our variables? Every unit of car A gives us $400. Every unit of car B gives us $300. So there's our profit. We're trying to make that as big as possible. What about our constraints? What are the things that are holding us back? Well, we had 4 things that are holding us back. We only have so much assembly time. We're told that car A takes 4 hours on the assembly line. Car B takes 6 hours on the assembly line. So by setting our variables, that is the total requirement on the assembly line that's needed to build the cars, and it cannot be any larger than 720 or else we run out of time. Finishing time. Car A takes 6 hours, car B takes 3 hours of finishing. We are told we only have 480 hours of finishing time, so that's what we require. That's what we have. We can't go over what we have. Now in this one, we have a couple of other things. We have that we need at least 20 of Model A and at least 30 of Model B. So that gives us 2 more constraints. Now, notice in this one, we normally talk about non-negativity constraints, that our variables have to be greater than or equal to 0. Well, in this case, we don't need those non-negativity constraints. We're already told that not only do they have to be bigger than 0, but they have to be bigger than 20 or 30 respectively. So we don't have those extra non-negativity constraints. But when you're putting together a linear program, always think about all your variables and do I need a non-negativity constraint here? So here is our overall formulation. Maximize our profit. We're told what the profit is for each car, subject to our assembly line only has so much time, our finishing line only has so much time, and we have promised to deliver a certain amount of each car. So now you can solve this. Again, take this, put it in the Excel solver, and see what you get. Make sure that you know how to use the Excel solver or some other solver. Now, when you solve this out, you should get an answer of x1 equals 30, x2 equals 100, and my profit is 52,000. Okay, so that is the solution to this car manufacturer problem. Let's think about a couple of other things. These are the types of questions that you often have to answer once you've solved something out. So, can a better profit be achieved if the minimum constraints are relaxed? So in other words, once you solve this out, there will be questions that come out of it saying, okay, what if I change my constraints? What if all of a sudden instead of 720 hours, I can get 800 hours? How does that change? Can I change my profit if I do that? And if yes, is it worth it? So if it costs me another $5,000 to change that constraint, is it worth it? Or am I going to be spending more money than I make back? Those are the types of questions that's, again, the sensitivity analysis that we're going to be getting into. If profits change, should the number of cars manufactured change? So in other words, if instead of making $100 on a car, suddenly economics change and I can make $120 on a car, or it changes that I can now only make $50 on that car, how is that going to change the answer? This is another sensitivity analysis. If I change something, in this case, if I change the profit for an individual car, how does that change my answer? That's a sensitivity analysis again. And if the availability of hours, I already talked about that. If the availability of hours change, how does that affect the optimal mix? This idea of sensitivity analysis we're going to get into fairly soon, but these are important questions when you're answering these things in the real world. Shipment problem. Here's another type of problem. We have a company that has a bunch of warehouses and a bunch of distributors. So they have to get their products from the warehouse to the distributor. So they have 3 places that are warehouses. They have 4 distributors, and they need to get product from warehouses to distributors, but there's all kinds of choices in what they can ship where. They could go from the 3rd warehouse to the 4th warehouse, or from the 3rd warehouse to the first distributor, or a mixture, or send stuff to all 4 of them. The question is, how can they do this for the least cost, keeping in mind some constraints? So this thing says that each warehouse has 20 units of an item, 30 units, 50 units of the items in the warehouses. So each warehouse only has so much stuff. Each distributor has certain requirements. So the distributor needs a certain amount, each warehouse only has a certain amount. So those are some of the things that are holding us back. We can't ship more than they need, and we can't ship more than we have. And then there's also the cost. These warehouses and distributors, the idea is that these are spread out all over the country. So it costs a certain amount to send something from each warehouse to each distributor because you're shipping at a different distance. So this says shipping this matrix tells us the amount, the cost. So shipping 1 unit from warehouse 1 to distributor 1 costs $22. Shipping 1 unit from warehouse 1 to distributor 2 costs $36. Okay, it's probably farther away, so it costs more. And so on for all of the combinations. And the question now is, how can I get what each distributor needs for the lowest cost? Keeping in mind that each warehouse only has so much stuff. Here's my variables. First step, what are the variables? Note that items can be shipped from each of 3 warehouses to each of 4 distributors. So that's 12 variables in this. All of a sudden, my number of variables is going up. So my variables are now going to be two subscripts. Xij is the amount of stuff I'm going to ship from warehouse I to distributor J. So X24, that is from warehouse 2 to distributor 4, for instance, the amount that I'm shipping. And there are 12 possibilities. There are 12 things I can control. So there are 12 variables. That's a common shipment problem. So what's my objective function? Well, remember my matrix had the cost for each of those variables. So my objective function, I am looking at minimizing my cost subject to this big long equation, 12 variables. What about my constraints? What's holding me back? Well, each warehouse only has so much stuff. Each distributor only needs so much stuff, and my non-negativities. So warehouse constraints. Warehouse 1 only has 20 units. Warehouse 2 has 30 units. Warehouse 3 has 50 units. So the amount of stuff I ship out of warehouse 1 can be no more than 20. So I get my first constraint. And then I get my constraints for my other 2 warehouses. I can only ship as much as I have. What about my distributors? They need so much. So that's a greater than or equal to. See, in this case, we have a mixture of less than or equal to and greater than or equal to. They require 20. I'm going to say I'm going to ship them at least 20. We're going to get into some of the subtleties about equal versus greater than or equal to later on. But for now, I'm going to say that they need 20. I'm going to ship them at least 20 units. So my first distributor needs 20. Where do they come from? They come from each of the 3 warehouses. The amount shipped from warehouse 1, the amount shipped from warehouse 2, and the amount shipped from warehouse 3 has to add up to at least 20. So that gives me my next 4 constraints. So in total, I get the 7 constraints for the distributor and for the warehouse limits. Finally, my non-negativity constraints. I can't ship a negative amount. So all of my variables have to be positive. And there's my linear program. There is the problem formulation in linear program. Now, feel free to enter this in Excel. You will need 12 columns for your variables. You will need your objective row plus 7 rows for your constraints, and you can solve this in Excel. But we're going to see that this kind of problem actually has a more efficient way of solving it rather than using the simplex method. There is a special method that can solve these problems, and we're going to see that later on in this course. But for now, feel free to go ahead and solve this if you want to get more practice with Excel. Finally, here's an investment problem, another standard type of problem that you'll often see with linear programs. We have $10,000 and 3 stocks. You can put that $10,000 in certain places. And the financial analysts have kind of figured out what the expected performance is of each of those stocks. So first stock. In the first year, it's expected to grow by 3.5%. In 10 years' time, it's 8.5%. Yearly dividend rate, 6%. In other words, it is going to pay back 6% every year of your investment. Stock 2 has those numbers and stock 3 has those numbers. So you invest money in it, the stock grows, plus it pays you some money back every year. They've decided to invest the minimum amount to meet certain goals. So right away, this should tell you that we are going to be looking at a minimization problem. Okay. And this problem is a little bit more complex in figuring out than the others. But we have the following goals. 4 different goals. No more than 10% of the investment can be in stock 1 for whatever reason. We need to get at least $400 in growth over the first year, at least $8,000 in growth over 10 years, and we want to get annual dividends of at least $150. That's our objectives. Those are the things we have to meet. So these are going to be our constraints. So the idea here is we want to do it. We want to meet these goals by spending the least amount of money. So we're trying to minimize our investment to meet certain goals. So our investment objective. Determine the minimal amount that must be invested in each of the 3 stocks to meet the stated investment goals. That's what we're trying to do. What are the things we can control? What are our variables? Again, write down what each of the variables mean. The only thing we can control is the amount of money we put in each stock. So we can put X1, X2, and X3 is the amount we invest in each of these stocks. Our objective function. This is what we're trying to minimize. We're trying to minimize the amount that we invest. And what is that? Well, that's simply the sum of the amount we invest in each stock. So it's a pretty straightforward objective function. It's just the sum of the 3 variables. But now what's holding us back? There was those 4 statements, plus a couple of other things that we need to take into account. First off, there is at most 10K to invest. So the total amount you invest can't be any more than 10K, 10,000. X1 plus X2 plus X3 has to be less than or equal to 10,000. The second one, at most 10% of the amount you invest has to be in stock 1. So the amount you invest in stock 1 is X1. The total amount you invest is 0.1, or is X1 plus X2 plus X3. X1 is no more than 10% of that. So that is the amount written out. But this isn't in our standard form that we're used to seeing. So let's rewrite it a little bit. We have X1 is less than or equal to 0.1, X1 plus X2 plus X3. And this is something you'll commonly do. You want to get just a constant on the right-hand side and all your variables on the left-hand side. So we can rewrite that as X1, taking everything from the right-hand side to the left side, minus 0.1 X1, minus 0.1 X2, minus 0.1 X3 is less than or equal to 0. Simplifying it just a little bit, 0.9 X1 minus 0.1 X2 minus 0.1 X3 is less than or equal to 0. There is our second constraint written out in the format we're used to seeing. That is the constraint that says only 10% can go into stock 1. What about our next constraint? Next year's growth has to be at least $400. Well, our chart said that we get 3.5% growth in year 1 from stock 1. So the growth we get in stock 1 is 3.5% or 0.035 times the amount that we put in. That's the growth we get in year 1 from stock 1. In year 2 from stock 1, or sorry, year 1 from stock 2, we get that much growth, 4.2%. And in year 1 from stock 3, you get 6.9% growth. So those things all added up tells you how much growth in dollars you're going to get in the first year. And we're told it has to be at least $400. The next constraint looks out over 10 years. So in 10 years, we want at least $8,000 growth. 85%, 40%, and 96% growth for the 3 stocks, and that has to be at least 8,000. So that gives us the 10-year growth that is expected from the mixture of stocks. And finally, the annual dividends have to be at least $150. That was our fourth constraint. That equation gives us our annual dividends, again, according to the chart that we had. That's the amount that each stock pays you every year, just for investing. Then finally, you have your non-negativity constraints. Well, you can't invest a negative number, so each of my variables has to be positive. And there's my constraints. All of that put together gives us this formulation for our linear program. Minimize subject to the subject to we only have so much money, the 4 stated goals, and the non-negativity constraints. And again, this is one that you can plug into your Excel solver and see what answer you get. So when you put this in your Excel spreadsheet and solve it out, you actually end up with something like x1 equals 0, x2 equals 0, and x3 equals 8,333 and a third, I believe. So it tells you that you want to invest everything in x3. So that's another example of problem formulation. Problem formulation, as I said, is a very important part of what you do for solving these problems in the real world. So thanks for paying attention, and next class we will be talking about the simplex method. What is the Excel solver actually doing in the background? And we're going to relate it back to the graphical solving that we saw in the first lecture.